Alright, I believe that's enough of the cartoon for today. I hope you appreciate it. I kind of relate with the teacher in the cartoon. I don't know if you relate with the student or not, but I got to look for that positive grade, D+, not a bad grade at all. Let's begin. 5.5, the trapezoidal rule. Now, ladies and gentlemen, I really like this lesson. We started out in Chapter 5, if you will recall, approximating areas underneath curve, and we did so with rectangles. Certainly rectangles were easy because of how you find the area of rectangles, but rectangles are not the most accurate. Of course, then we progressed on into the chapter and I went to exact answers, not using rectangles, but using the fundamental theorem of calculus. Let's go back and let's revisit the idea of approximations. There are two more approximation methods that we will use. One, the trapezoidal rule, which is currently a standard on the AP exam. The other one is Simpson's rule. Now, Simpson's rule is not quite as important in most calculus books. In fact, it doesn't even get mentioned in the title now. I don't know why people are moving away from it. But the trapezoidal rule, as you're going to see, uses, as you would guess from the name, trapezoids to approximate the area underneath the curve. Simpson's rule actually uses rectangular shapes with curves on top, so like a rectangle and a semicircle together. So that's what we're going to look at today. And we will start with the trapezoidal rule. So imagine, let me move the screen just a little bit. There we go, I think that'll work right there. Imagine you've got this very irregular shaped curve right here, and we want to find the area underneath it. Well, again, rectangles based on the steepness of the curve at points would not really give us a great estimation. But look at how accurate trapezoids are. Now notice that trapezoids are not perfect, but they're much better than what rectangles would be. In fact, you can even just by the shape of the graph make a guess as to whether or not your trapezoid will be an overestimate or an underestimate. For instance, if you're talking a positive graph, so you see here we're above the x-axis. If your graph is concave up like this one is, you see that the trapezoid extends outside of it, so it's an overestimate. If, however, the graph is concave down like here and here, you see the trapezoid comes up short and it's an underestimate. Then we come down here, it's the same principle. You say, well, now, wait a minute, this one's concave up, but it looks like an underestimate because there's gaps here. But remember, we're talking about negative area, and a smaller negative number is still a better shape than what a positive or a bigger negative number is. So the principle still applies. If you're concave up, it's an overestimate. If you're concave down, it's an underestimate. This one would have less negative, therefore an overestimate, as opposed to what we would have up here. So what is the trapezoidal rule? If you take your integral from a to b f of x dx and you break it up into subsections and you make your trapezoids, this is how we approximate the area. We start out with b minus a over 2n times f of x sub naught plus 2f of x1, 2f of x2, all the way up to 2fx to the n minus 1 plus fx to the n. So here essentially is what's happening. You've taken your interval from a to b, you've broken it up into a partition. Maybe you've broken it up into fourths or tenths or 20ths, however many trapezoids you want to draw. And each endpoint, now this is not just left endpoint, right endpoint, but at each of those endpoints of the partition, first of all, you plug the first endpoint in to the function. Then you go to the next endpoint, plug it into the function times 2. The next one into the function times 2, and so on and so on and so on until you get to the last endpoint, which you do not multiply by 2, you just plug into the function. Again, B and A represent the endpoints. N is the number of trapezoids that you want to use in the approximation. And I will go ahead and tell you, yes, there is a program on your calculators that will do this. It's called numerical area. I will show you when we get to the end how to use that program. But let's work some by hand first. Alright, applying the trapezoidal rule. We are going to estimate the area underneath x squared from 1 to 2, and we're going to do it with 4 trapezoids. Now, if you want, you can take the time to make a sketch of this if you want. I'm not going to. I'm going to go straight to the trapezoidal rule now. Now, let's look where all these numbers come from here in our rule. First of all, you see the a and the b value are 1 and 2. So b minus a over 2n. N is the number of trapezoids we're going to use. We're going to use 4. The 1 and the 2 are right here and right here. That's always the case. This is always your a value plugged into the function. Now notice the function is x squared, so a squared. This is always the b value plugged in to the function, b squared. So how did I come up with these numbers right here? Well, remember I'm starting at 1 and I'm going to 2. 1 to 2 is a distance of 1. And I'm breaking that distance of 1 into 4 equal parts. So 1 divided by 4 is 1/4. So I take 1 and I add 1/4. 1 plus 1/4 is 5/4. Add 1/4 again, you get 6/4, which is 3/2. Add 1/4 again, 7/4. Add 1/4 again, 8/4, which is 2. I take each of those then and I plug them into the function. Remember, the endpoints stay as they are plugged in. The middle ones get multiplied by 2. And then it's just a matter of working all this out. That would be 1/8 on the outside. This becomes 25/8, 9/2, 49/8, and 4. Add all that up, you get 75/4 times 1/8, and we get 75 over 32, which is approximately 2.34375. Now, is this an overestimate or is this an underestimate? Well, let's see what the exact value is. The exact value, if you take this and you solve this using antiderivatives, gives us 7/3, which is 2.3333333. Now, you see that our answer is bigger. It's an overestimate. How did I know it would be an overestimate? Because this is concave up, and we said that if it's concave up, the trapezoidal rule is an overestimate. Now, this brings us to an interesting problem, and I'll go ahead and tell you, I've seen several of these on the AP exam. Average temperature. An observer measures the outside temperature every hour from noon until midnight, recording the temperatures in the following table. So at noon, it's 63 degrees. 1 hour past noon, it's 65 degrees. So at 1 o'clock, at 2 o'clock, 66, 3 o'clock, 68, all the way up to midnight where it's 55 degrees. What was the average temperature for the 12-hour period? Now, most people would be very tempted to take all the numbers, 63, 65, 66, all the way to 55, add them all up, and divide by the number of numbers, which in this case would be 13. Well, sadly, that doesn't work, because average in that sense really only deals with discrete values. Discrete values are where you have a point, and then you have another point, and another point, and none of them are connected. But if you think about temperature, it doesn't go from just 63 degrees at noon to 65 degrees at 1 o'clock. There's that gradual procession from 63 to 65. And then there's another gradual procession from 65 to 66. So we have to take into account all of those middle numbers also. So we are going to use the trapezoidal rule to do this. But now notice it's not just the trapezoidal rule because it's average temperature. Now think about what that average means. Well, we have done average with integrals before. So here's what we have. The average temperature, the average amount, remember, is not just the integral from a to b of f of x dx, but when we do average, we do this 1 over b minus a part on the outside. So if I take that 1 over b minus a and I apply it to the trapezoidal rule, which is from here all the way over, I see that there's some change I can make here. See the b minus a and the b minus a here. I can cancel those out. And so for this problem, I'm actually going to use this formula. 1 over 2n, and then the rest of it is the same. All right, well, what would f of x sub 0 be? Well, that would be the first temperature right here, 63 degrees. And then we have 2 times f of x sub 1, so that would be 2 times 65. And we have 2 times f of x sub 2, so it would be 2 times 66, all the way up to 2 times 58, and then 55. Now, if I may just, for a very brief moment, why is it 2? Why is it 2 in the middle? Well, imagine making a box from here to here. All right, well, there's a 63 and a 65. Then we make another box from here to here. That's a 65 again and 66. So you see the 65 got used twice. And then another box here to here. So that would be 66 again. It got used twice. And so every number when we make those boxes gets used twice that's on the inside. Only 63 and 55 on the end don't get used twice. That's why they don't have 2's on the end. So I'll take those numbers, I'll plug them in. Again, there's my 63, 65 times 2, 66 times 2, and such. All the way up, although I have a typo here, that should not be 2 times 55. That should just be 55. And n, how many numbers do we have? It's not the number of numbers here, it's the number of boxes that we would use. In this case, the number of boxes is not 13. the number of boxes would be 12. There's 1, 2, 3, 4, 5, all the way up, and that would be 12 boxes. But again, that should not be 2 times 55, and the answer does come out to be about 65.17 degrees. Please make sure that it does on your calculator. If it does not, try dropping that 2. I don't remember if I dropped it or not when I did the calculation. But know that the 2 should not be on the 55. Alright, let me move our screen here. Simpson's rule. Now, Simpson's rule, again, does not use the basic trapezoid. It instead uses curves at the top. It looks like a box. You see down here, it looks like we're using boxes. But instead of having the diagonal top like a trapezoid, it's got this nice little curve shape on it. It's a nice little proof if you want to look in your book, or you can just take my word on it. But Simpson's rule is a little different from the trapezoidal rule. Instead of b minus a over 2n, it's b minus a over 3n. Notice it's still f of x sub 0, it's still f of x sub n, but notice on the inside it alternates 4, 2, 4, 2, 4, 2, 4, 2, and then the last one has to be 4. Now that does mean that there's a certain number of n's that do not work. Some n's will work, some n's will not work. In fact, I will tell you now, if you have an even number of n's, this will work. An odd number of n's, Simpson's rule does not work, because you have to have a certain number where these 4 and 2's will alternate, and it starts in 4 and it has to end in 4 also before you go to the last one. Trapezoidal rule, you can use an even number of n's or an odd number, it doesn't matter. But Simpson, it has to be even. Alright, let's work a problem. Applying Simpson's rule. Use Simpson's rule with n equals 4 to approximate the integral below. Alright, we have 0 to 2 of 5x to the 4th dx. So again, just like with the trapezoidal rule, it's a matter of plugging in numbers. Alright, so b minus a over 3n, right there. And notice I take my endpoints, 0 and 2, and I plug into the function. So there's 5 times 0 to the 4th, 5 times 2 to the 4th. Now the rest of these, you say, well, how do you get these numbers? How am I getting the numbers that I'm plugging in? Well, first of all, notice that we alternate 4, 2, 4, as we're supposed to. And the rest of these are 5x to the 4th with the different numbers plugged in on the partition. How do I get the numbers? Well, I'm going from 0 to 2, but I'm breaking it up into 4 parts, so that's a distance of 2 divided by 4. So each jump is 1/2. So if you start at 0 and jump up by 1/2, you go to 1/2. Jump up again, you go to 1. Again to 3/2, and then again to 2. And from this point on, you can just multiply all that out and work it out. We do end up with 385 over 2 on the inside. On the outside is 1/6. So we have 385 over 12, which is about 32.083 degrees. I don't have any nice little rules about Simpsons as far as over or under estimations. It's not quite as simple as it is with the trapezoidal rule. Best way on those, if it asks you, is to just calculate the exact answer, and then from the exact, look back at the estimation, and then decide that way. Alright, error bounds. Now, ladies and gentlemen, on this one we're going to use the calculator. It says use the trapezoidal rule and Simpson's rule to approximate the integral below with n equals 4 and compare the answers to the actual area and decide which is more accurate. Now, what I'm going to do here, I'm about out of time on this first video. I'm going to go ahead and stop this video, and when we start the next video, we'll start with this problem, and we'll start going back and forth with the calculator. Alright, so I'm going to stop this video, and we'll start the next one in just a second.